these compact loops. So let's review what we're doing. We're looking at the classical compact loops. And we began our study by looking at a real vector space. In fact, I'm quite happy to do it in a basis if necessary. Of course, finite dimensional in my case. And a symmetric positive definite inner product by linear form, so that the norm, which should give us the geometry with respect to this inner product, is just V with V. And it's good enough to consider at the beginning anyway, V to be the vector space Rn, and this inner product, we say two vectors here, V, which we write as a column vector, V1 to Vn in the standard basis. The inner product then is written in a very nice way, computationally, as just V transpose the row vector times the column vector. So that's the nice symmetric inner product. And in a standard basis, this gives us, so if we have V equals x1, e1, plus and so on, xn, en, and then we write this equal to x as a column vector of numbers, and then v w and y is to say is, and w is the same thing with y, y1, e1, and so on. Then VW, the standard inner product, is just x transpose y, which is x1, y1, and so on. I mean, you knew this, I'm just warming up this morning. And of course, the norm of a vector, then the norm of v squared is x transpose x, and that's just sum of the xi squared. So if you don't have much experience with linear algebra, you can just think 2 dimensions and close your eyes and just make the sum. It doesn't matter if 3 dimensions. It's no problem. So that's a situation, and then the symmetry group which we call ON, which is contained, it's contained in GLNR, so I'm considering a group of linear symmetries. And I might add that if you have experience in mathematics, you know that in applied mathematics, physics, and so on, people linearize all the time. In calculus, you do too. You look at the linear part of a function, and it's called the differential, right? So, nonlinear mathematics is a new ballgame. So quite often we try to reduce to a linear situation through a linearization procedure. Nonlinear mathematics is realistic and very, very important. In some cases, let me just comment on that. If you take the most obvious question, which you probably know about, if you're interested in the flow of water flow, or the flow of air across a wing of an airplane, or or whatever. There's a famous equation that's called the partial differential equation, which is called Navier-Stokes equation. You've maybe heard the word, Navier-Stokes equation. This is slightly nonlinear. If you would write it down, it's slightly nonlinear. Only slightly nonlinear. And you cannot prove, so far it has not been proved that this equation has a solution. You understand what I'm saying? My friend told me, you cannot prove that an airplane flies. That makes me a little nervous, but because you cannot solve the Navier-Stokes equation, you cannot prove that it has a solution. Now, numerical analysts do good things to get some approximate thing going on there, but you cannot prove. It's just a little bit of nonlinearity makes life really different and interesting. So keep that in mind. But here we start with the linear symmetry group for historical reasons and also because we linearize quite often. So we really need to understand this linear symmetry group. It's there and we know what it is. I mean, it's a set of operators. So it's in this, say a transformation is in this group, if and only if it preserves the structure. And quite frankly, if we're doing over R, I said it's good enough to look at this form, which is the standard form over there. So let's look at this thing, and that means that in fact, this is, if you write it down, this is V transpose T transpose T W, and this is supposed to be the same as the original pairing, which is just V transpose W. So what that says is that T transpose T has to be the identity. And we have other ways of looking at this. I explained this in great detail yesterday, but I just want to say that that's a very interesting equation. And I want to tell you how to look at this equation. I guarantee this is how to look at this equation. We define sigma of T to be equal to T transpose T. No, excuse me, T transpose inverse. Yes. And now look at the fixed point set of sigma. Fixed sigma means if you fix a transformation T, then that means that T equals T transpose inverse, and that means that T times T transpose, or transpose, it doesn't matter on which side it is, equals the identity. So what we have learned from this little detour, so we made a detour here. Detour. German word of detour, Umleitung, it means it's leading you around something. So that's detour is much better. You could just say it's a little detour. German is leading you around. That's in Germany you see there are so many places on the streets and so on where you have to go around because they're working there and the street has been blocked. And it makes me crazy. Well, particularly in the train. Yes. You try to go from Bremen to Münster, which I have to do quite often. And there's a detour way around Germany, almost to Holland. So it's ridiculous. So this is a little detour, Umleitung, that I said. I said, what you really ought to do here is look at this guy, which is an operator. It is itself an operator. So let's look at that. So it says that the conclusion is that the fixed point set of T of sigma is equal to the orthogonal group OM. So somehow or another, with all this geometry, this entire blackboard here of discussing orthogonal group and this, that, and the other, results after you've gone through this detour is you start with GLNR and together with a thing sigma, and this defines the orthogonal group. OM. Got it? Yeah.
Can you define again what you mean by sigma? Or sigma was taken from what?
So, yeah, let's go very slowly because this is sort of your first time looking at something like sigma. Okay? Again, let's look at the motivation. It's not motivation, it's just fact. I'm trying to write down what it means that it preserves the structure. And it means that this thing is the identity. But another thing it means is that this, I mean, there's no difference. Right? That's what it means, that T equals T inverse transpose. And now you have, because you just bring that on the other side, you get the equation, right? But you see, what is behind the scenes is a mapping that takes T to T inverse transpose. This is a mapping. It takes it, right? You can imagine what this mapping is. It's slightly non-trivial, right? I mean, you can imagine, take the inverse of this matrix, that's horrible, and then take transpose. Okay. So I introduced this because that's obviously the fundamental operator behind this scene, because the fixed point set of this operator is exactly the orthogonal group. Okay? I don't know about, Nicholas, what is your question?
No,
I just introduced it because I want an operator that defines this situation. Instead of going blah blah with the scalar product and all of this stuff, I reduce everything in the discussion to this kind of operator. It's not a bad idea, right? It's very simple, right? It's not my idea. The idea is almost certainly from A.D. Cartan. So that's it. So in other words, you start with, let me repeat what I said, you start with GLNR and a sigma. You know what sigma is? It's a mapping from GLNR to GLNR. It's a mapping. And let's, and in fact, I wrote it down for you. Sigma of, if you like, a matrix is matrix inverse transpose. And what we have here, this is a statement on one little blackboard. The fixed point set of the sigma is the orthogonal group. So you really have the orthogonal group defined in a beautiful way. And so it says we should look at this operator. I think maybe that's what Mr. Weiss is asking. Well, let's look at this thing and try to understand what the devil it means. So we look at sigma. And the first thing you should look at in my mind is what is certainly, it's certainly not additive, but let's look at what sigma of AB is. Sigma of AB is AB inverse transpose. This is B transpose A transpose inverse. And this is then A inverse transpose B inverse transpose. Do you get it? You've done this calculation before. You haven't had much experience what it means in linear algebra, but I mean, I just wrote a brutal calculation for the fact that this is a multiplicative homomorphism. Yeah. It says sigma of A, B, is sigma of A times sigma B. This is sigma of A, B equals sigma of A, sigma of B. That means it's multiplicative, yeah? Right? And so this is what we call, it's with respect to the multiplication in the group GLNR. This is a group GLNR. This is sigma is a mapping from GLNR to GLNR. It's a mapping. See, we have a group and we have a mapping, which is a homomorphism because of this property. It's a homomorphism. and then you study it a little bit more, and you apply it twice. Sigma of A. I hope you can do that. I mean, at nighttime when you can't do anything else, do a calculation like this. That's sigma of A inverse transpose. And that's A, yes, that's A inverse transpose. So you do it twice. I hope you see that's just A. Right? So if you do it twice, you don't do anything. Well, that says that we use the word that sigma is an involution on the multiplicative root G and R. So we learn just from the simplest considerations that very interesting, all of this geometry and all of this, that, and the other, really what's playing something in the background is an involution, so I just want to mention it. Once you see that, you should keep your eye open in mathematics and physics for involutions. Okay. And now I want to speak about what everybody does in life. So life. So first of all, life is quite often studying these operators. So we have some matrix A. Let's say is in G. Let's just take an example in GL2R. And you learn to understand that that means that A is a mapping from R to R, linear. And then what you learn to do is you want to learn to look for invariant subspaces. Oh, R to R, I'm sorry, R2 to R2. You look for invariant subspaces. So there's may or may not be any. Oh, thanks. So invariant subspaces, it means, in this case, there's only one-dimensional invariant subspaces, so let's call it L for line. So you look for invariant lines, and maybe you could decompose this operator into better spaces. Maybe it has an invariant line here and an invariant line there, and then we understand this operator very well. So what this, here's L, and then there will be, it means that if you have a vector in L, that it gets mapped to some multiple of this vector in L. So it means that A of V is some multiple of V. That's what it means. And so by the way, these Germans, it was very difficult, I guess, at the beginning to get notations. You say V is an eigenvector. You have to think the German word for vector is vector, and the German word for eigen is eigen. And the meaning of eigen probably is own or proper. There are several meanings here, you have to think of it. I don't like, if you translate this, the German word eigenvector into the English translation, proper vector, own vector, all these things, it sounds really stupid. So therefore we left this in German in mathematics. It's called an eigenvector. You know it all. And lambda is called an eigenvalue. But physics people know that this means an energy level of something. Yeah, right? So this has deep physical meaning, and we were interested in all this, and this has led to the spectrum of the operator, which is a set of eigenvectors, eigenvalues. on this blackboard, I wrote the word life. You don't object. If somebody hands you an operator, you say, I want to look at a simpler operator. Just mathematician, not some deep thing like physics where you look at energy levels and all that. And simpler would mean you look at some invariant line, and along that line at least, it's just a stupid operator. It's multiplication by a constant. It's dilation or contraction along that line. So you do all this, and then you learn to compute eigenvalues. You learn to compute eigenvalues, and you learn that the way to do it is you take you write down something called the characteristic polynomial of the operator A. Well, maybe as a function of z. I'm using the word z, letter z intentionally. A should be something like the determinant of depends how you want to write it. Maybe z times the identity matrix minus A. Something like that. Something like that. And the motivation for that is that this guy has if you're incredibly lucky, this is an R2, I mean, it doesn't matter. If you really find a basis of eigenvectors, so V1 is an eigenvector and you get lambda 1, and V2 is an eigenvector and you get lambda 2, then here if you look at Z, I hope I did it right, Z identity minus A would be here, so it's Z minus lambda 1, Z minus lambda 2 here. And then the characteristic polynomial is the determinant of that thing. So you see what it is, and this characteristic polynomial doesn't depend on the basis, you check it. So then what it really is the product of Z minus lambda I, where in this case I equals 1 to 2, where they are the eigenvalues. So you find the eigenvalues as the zeros of the characteristic polynomial. Yeah? Of course, there's no particular order, and the symmetry group acts, and so on and so on. Right. So just to remind you that if you're having fun, that this is, in this case, it's z squared minus the sum of the eigenvalues, so that's the first symmetric function of the eigenvalues, z plus the second symmetric function of the eigenvalue. Of the eigenvalues, where lambda 1, lambda 2 is the eigenvalue there. Okay? So the appropriate invariants of this situation are C1 and C2. It doesn't depend on the operator. And then you check and you find out that, and you ask, why the devil did he introduce the word trace? And then you ask, okay, you know about determinants area, and so this is the determinant. Okay. So, and in modern mathematics, these are very important invariants, curvature invariants of differential geometry, for example. It's a very serious subject here. So at the beginning of this serious subject, you look at a 2x2 matrix. You ask if you can, you ask for invariant vectors. They're not invariant. The line is invariant, and it's just along that line. It's just multiplication by a constant. Physicists told you that those things are really important because you can interpret them as energy levels in some system. So you say, I'm getting excited about these things, and so you define the spectrum of this operator to be the set of eigenvalues, and then you figure out that you can calculate this set of eigenvalues by solving an algebraic equation, which is very easy to write down. And if you write it out, the coefficients of this algebraic equation are very interesting. Trace and determinant. And what I did here, of course, is the 2 by 2 matrix. Now life is not 2 by 2. Life is very big dimensional. Yeah. So well, you have so let's say that A is an operator in GLNR. And you immediately say that obviously eigenvalues are important. So you write down the spectrum of this thing, this operator. These are important things for physics. And this is the zero set of the characteristic polynomial. The characteristic polynomial of A in the variable z, and that's it. Yeah, and it's very interesting because you write this down, this is z to the n minus c1 of A, that's some invariant, doesn't depend on the order of the eigenvalues, z to the n minus 1. The permutation group immediately appears here due to the fact that you really are looking at the roots of this characteristic polynomial, and so these things are very, very important. Right? Here's the determinant. If you ever want to know, well, that's the determinant. Here's the trick. And probably you've never thought about what's in between. I'm willing to bet you. Maybe you, but nobody else. Right? What are the invariants in between? It's interesting, right? Not just the trace and the determinant and so on. What else is there? These are curvature invariants in Riemannian geometry. Okay. If you really are talking about the appropriate operators of Riemannian geometry. This is relatively new mathematics in Riemannian geometry, in my mind, underlined by a wonderful mathematician by the name of Chern. Let me just write his name so you see it. Chinese, maybe I've mentioned before, who actually has great German roots, studied in Hamburg, and then went back to China, and people were really worried about him in the Second World War because the Japanese were, I love Japan and I love my Japanese friends, but in the Second World War they were being very brutal in cities like Nanking and so on, really killing everybody. Okay. And everybody worried about Chern was going to get wiped out. But he was more or less sheltered and was able to come back to the United States. So let me just write here, Hamburg. His teacher was Blaschke. Maybe you spelled Blaschke like that, I'm not sure. Blaschke. And then China. Back after Hamburg, going back, and then he was professor for many years in Berkeley, California, where we hope some of you graduate students can go. It's a very nice place. And of course I knew him rather well, so that tells you the age of this. He's of course another generation, but a wonderful man of great culture. And he understood the role how to use C1, C2, and so on, Cn, in what is called a differential geometric setting. But the original thing that happened here is, well, either you're talking to physicists about energy levels, and those are eigenvalues, or you're just a mathematician who's saying, I'm looking for invariant lines, and then on that line it's a trivial thing. You immediately get to the characteristic polynomials, you immediately get to these coefficients, you immediately ask what the double do they mean. Right? Well, I hope you are amused by these things, and so you take this operator that I like very much. I'm going to take the operator to look like this. It might have a different sign than what you took. The reason I am taking this, so look what happens here. E1 goes to E2, and E2 goes to minus E1. So that means, in fact, this is rotation by pi over 2 in a positively oriented and usual orientation. So this operator, if it takes a vector v, it rotates it into j of v, which is positive rotation from the point of view of the standard orientation of R2. If it's negative rotation, I think maybe I had it's minus or something. This is a fundamental operator of the first course in physics. You will tell everybody in this room who studied a little physics knows this is a fundamental operator. In fact, let's write down j squared first of all, is minus the identity. That's looking good. Yeah. And now let's look at it. Let's look at it in space. So let's take what our friends in classical mathematics have done. They take a vector v, and then depending on v, they add it. So they look here at j of v. So it looks like this: j of v. This, I hope you understand this picture because it's not correct. A vector in engineering mathematics and physics has its foot at the origin, right? Yeah, but you can think of it any way you want. This transformation could act on tangent vectors here. Okay, so you see what this is. It takes v and goes to j of v. Okay, that's the way you should think about it. You take v and then you follow this by j of v. And it tells you what you get, and so on. And then maybe you go over here and you have w, and it tells you that what you do to get what j of w is. Right? You should get a feeling of rotation, I hope. Feeling of rotation. So some feeling of rotation. That's very interesting. And now we're mathematicians, we say, well, we want to understand that operator, so we look at the spectrum of that operator. What are the eigenvalues of that operator? Right? We're looking for stable lines. Now you should see, of course, this is obviously a rotation. There's no such thing as a stable line. If you take a line, you rotate it out, I mean, by 90 degrees. So intuitively, in the background, you look at intuitively, no stable one-dimensional subspaces. And you compute that, and that is you set the characteristic polynomial of this guy of this operator j to 0, and of course you see what that is. Let's look at it. That's the determinant of, let's write it down, the matrix z here and z here. and then minus the operator, so that gives you minus here, and plus here, yeah? And that is equal to z squared plus 1 equals 0. Right? So by considering geometric things without thinking about the complex numbers, you were forced to look at complex numbers. Right. So we are forced to look at complex number. There's no such thing as a stable line for this operator. C. And in Mickey Mouse mathematics, you have learned to compute the eigenvalues by some stupid procedure. And if I give you a random matrix, well, not random in the sense of probability theory, but I pick some matrix out of the air, and it'll drive you crazy to compute the zeros of that characteristic polynomial. It's a numerical analysis problem, really. It's not so obvious, right? It's the idea you want to diagonalize the matrix, and it's a hard problem to physically really. So it's not so easy. And not only that, you're getting complex things, so it's really very non-trivial. So what God taught us to do in life, this is life followed by God. This is all God-given. This is I don't justify it. I'm being cynical. I have nothing against religion or anybody, but it's canonical in the sense of canonical. A canonical thing to do here. Canon. I told you that's music for me, but it's canonical. It has to do with the Bible. If you look at it, it's a Christian word, I think. Latin probably. Canonically, you look at complexify R2 to get C2. Okay. So you are forced to do that. So our great giants of the past did that, and so they had to figure out what is this object. So V is a complex vector space. And I don't know, C from V to V is an antilinear and of course non-degenerate, I guess, involution. What does it mean antilinear? Anti doesn't mean I'm against something, it means the opposite of something in this sense. Complex vector space over C. So this is over C. So this antilinear means with respect to C. So that means C of IV is equal to minus I of CV. Otherwise, it's real linear, but it's complex antilinear. Real linear, but complex antilinear. And then you look, it's an involution. So C squared is the identity. Right. And then you look at fix of C. It's an involution, right? You do it twice, you get the identity. So you have this great idea of looking at fix of it. I mean, what is the fix of it? This is what we call the real points of the vector space. Okay. So, in fact, the professional mathematicians, I think, generally say you never really complexify a vector space. What you're really doing is looking at a complex vector space with a notion of complex conjugation, which defines the real points as the fixed point sets of the complex conjugation. Well, you know that. In coordinates, you know this. Right? And in fact, if you say this is a basis of the fixed, this is the real points, you check it's a real subvector space of half the dimension over the reals. If this is a real basis, then you easily check that this thing is a real basis of VR. This is a real basis of VC of the complex vector space, and in fact, this is a real basis of VR, and it is also a complex basis of V. This looks a little fancy. It is not fancy. You just have to write it down for yourself. Yeah. So a real structure on a complex vector space is that. Okay? Is that. So this is a real structure as above. Oh, C as above is called a real structure on a complex vector, on the complex vector space. V. Okay. Okay. And now, if you have an operator like J, which appears everywhere in beginning physics, yeah, you agree? Everywhere in beginning physics, it should. It's an important operator like J. Then you start with J in physics or mathematics or whatever it is, and you say, okay, J, just like I did before, J of E1 equals E2, and J of E2 equals minus E1, and so you write the matrix 1 minus 1 J, that's J, matrix of J, so you write it down. That's rotation by 90 degrees. You're very upset, you get very mad. For example, I could get mad at my wife if I first discovered this and couldn't sleep. I would blame her for it. No, I get mad at myself. I don't understand what's going on because the spectrum of this thing is plus minus I. And it makes absolutely no sense over the reals because it's a real operator and having a spectrum plus minus I makes no sense, right, over the reals. So what you have done every time in Mickey Mouse linear algebra, you have implicitly transformed J to the vector space V to V. The complex vector space. You didn't tell anybody, and you just close your eyes and you say it's real linear, and I can extend it to the complex vector space as complex linear. Yeah, I just did it for you here in the basis. You need to think about canonically how you do it. If you have this is a basis of the real vector space, it's also a basis of the complex vector space. It's the same matrix. Only it's a matrix or an operator on the complexification or on V. Is extended to V as complex linear. Right? Right? And now we are interested in decompose, look at invariant subspaces of V. Invariant lines in V. But these lines are complex lines. because it doesn't make sense to talk about real lines. I'm talking about complex one-dimensional subspaces. Okay, let's do it. So you have this operator J is from V to V, and now let's see, J has the matrix. This is the matrix of J as a complex operator, and now let's see, and the eigenvalues are plus minus I. Okay, and now let's see if we can find the eigenvectors. You're probably better at this than I am. So I think, let's see here, let's see, what are the eigenvalues? Let me just try to see, maybe this is an eigenvector. I'm not sure. I've done this, you can do this, you know, you've been forced either in engineering or applied science courses to find eigenvectors. I think this might be one. Let's try it. J of this thing is E2, E1 goes to E2, and E2 goes to minus E1, so it's E1. And I hope this is I times this vector, right? Is that true?
Minus.
I times E1
It's minus I.
minus I. I hope it's, is that correct? So that, yeah, obviously it has to be minus I, and minus I times plus I is plus 1, and so I get that. Okay? So you see, if I call this vector maybe E plus, then I have E plus, J of E plus equals I minus I times, I won't call it E, okay, E plus. Maybe I'll call it E minus because the eigenvalue is minus I. There's no such thing as a well-defined minus. I call this E minus, and I times E minus. And if I'm not mistaken, E plus I'm going to define as the complex conjugate of that. If you have a polynomial with real coefficients and it has a complex root R, then the complex conjugate of that root R is also a root. Bar is also a root. So the characteristic polynomial equation, I wrote it someplace, is z squared plus 1 equals 0. So the complex conjugate has to be a solution. So plus and minus I have to be solutions. And let's see, J, this I wrote, I hope, yeah, it's actually true. I know this from geometry. The plus thing is most naturally the thing with the minus thing here. Let's see what happens. Let's hope that I get this right by J. E1 goes to E2, and E2 goes to minus E1. That's plus I E1, and this is indeed I times E plus. So you have a picture which I draw like this. Here is E plus, and here is E minus. They're probably even orthogonal, and they are stable lines. So J maps E plus into some multiple of E plus that happens to be a complex multiple I, and J of E minus goes to a complex multiple. You understand this picture in a complex vector space over the reals. Those things are copies of the complex plane, of the real plane, right? So this is stable. This is a stable C. I'll call it a C line, and this one is here, and this one is here. Okay. So you are forced for many reasons, to complexify your real vector space. You have never really explicitly said that before. In Mickey Mouse linear algebra, you are told by somebody to compute eigenvalues of a matrix. And you realize that there are matrices with complex eigenvalues, and you write it down and do everything over the complexes. That is Mickey Mouse because you don't know what you're doing, but on the other hand, it's correct. You simply, without saying it, just complexify the vector space and do everything in the complexification. Okay? Now, I know fortunately, I'm getting older, most of my friends are older and die and so on. So the person I'm thinking of is a wonderful person, a great mathematician, who said in a nice lecture in Hong Kong, which I was present, there is no such thing as a real vector space. Okay? A real vector space is a pair. Yes? A complex vector space and a definition of the reals by the anti-linear involution, which is called complex conjugation. Okay. It's a very nice remark. There's no such thing as a real vector space. The correct object is the complex numbers. And the reason is, of course, the fundamental theorem of algebra. Start with some field, whatever it is. You're doing calculations over that field. Most of the calculations end up in something like a characteristic polynomial. And then you've got to solve that thing over the field. You can't. The field's too small. So you look at what is called the algebraic closure of the field, which puts in all the roots of all the polynomials. So it's and then you have to say what's the algebraic closure of that. So when you get really tired, but you prove some theorems that everything's okay. Okay, so we start with the C as above, and of course we start with geometry. Geometry on VR, real geometry, because that's our world, Euclidean geometry, real geometry on VR. Well, what this is a scalar product, R bilinear. That's real geometry. That's a real norm. That's a real angles. That's real. Okay? And you extend this to the complex. So let's think about how you want to extend to the complex. And you extend to the complex. Now, Prabhat couldn't come today, but his justification in any discussion I'm going to make is something about do it in a basis and so on, and I think he's right at first, so let's do that. So let's take basis E1 through En, a basis of VR over R. And E1 through En is in fact a basis of V over C. right? If every real vector is a real linear combination of these things uniquely, then every complex vector is too. I mean, it's just the same statement, right? If you want to be brutal about this, then if you have a vector v in the complexification, then you write v is you can write v equals zi ei, where that's a complex number, and then that's zi is equal to x. I is always terrible, so if you have complex numbers hanging around, you should use alpha here or something. G alpha, so is this z alpha is equal to x alpha plus, now this is complex I, y alpha, right? And so this vector is x alpha e alpha plus I y alpha e alpha. So every vector is written in the complexification, which is twice as big as a combination of these two things that we considered before. Right. So that's right, and so that's an obvious thing. And now if you have the scalar product, this thing is on VR. Let's say that's the standard, some standard scalar. It's real bilinear here. And it's real bilinear. It's bilinear on these on both of these things here. Bilinear real product, right? And let me emphasize bilinear real product on R. This extends immediately to a bilinear product on V. A complex bilinear product on V. C bilinear on V. Well, I'll tell you how to do it in a basis, and then you can do it functorially. Yeah? You know what it is as a real bilinear form on the basis over VR, and you just force it to be complex bilinear on the basis of over the complexes. Let me do it one time because you've never done it. So if you have a vector in two vectors in VR, then you write them equal to x alpha e alpha and y, let's write beta here, e beta, same thing, right? And now you to the scalar product of these guys, VW, you just write down what it is. It's x alpha y beta, because it's linear in both factors, y beta of e alpha e beta. This is called the matrix of the bilinear form. Right? That's how you do it. You take a basis and then you write down the matrix of the bilinear form. Now I just close my eyes and say these are complex numbers instead of real numbers, and this gives me a complex bilinear form on the vectors, complex vector space. I just close my eyes. I don't have my glasses today, so it was very easy. Just close my eyes. Those are complex vectors, so close eyes. So this gives you, if you write x and y over c, it's the same thing. So it's purely formal. To start with a real bilinear form over the real numbers, and you get a complex bilinear form over the complex number. That is absolutely canonical. Okay? Okay. Now, what is also canonical is that if C is the real structure, on V, so that defines the real structure, then if you on V, then this extended thing, I'm not going to write it anymore, because it's going to be complex. This is going to be So I'll just say this. This is going to be the complex bilinear form. I look at C, V, C, W. So that's not the complex numbers, that's just applying that. This is complex conjugation. You immediately see this is exactly VW bar. Alright. That's very interesting. CV equals CW is VW bar. Okay. That's interesting. And so you think of these nice properties of this extended thing. CV, CW is W bar. So let's have an idea. I'm going to define now an interesting form, which I'm going to call H of VW as equal to VCW. Now, this may not be motivated, but let's look at it. Let's look at H of VV. This is VCV. Yeah. And let's do it in a basis just to convince you so what's going on here. So if we write V is, well, can we compute that? Anybody want to compute this for me? What that could be? This is a little bit mysterious because what we're doing was we're trying to pick up the real structure. I'm trying to get this real structure going here. See, we have here the real form, and here we have I times the real thing. And we would like to have this extended Riemannian structure, this extended bilinear structure here on the real points, the same as on the imaginary point. And I claim that this operator is really the good one to do it. So let's just see what happens if we write V equal x1 x alpha E alpha plus y it's always better to write y beta times I e beta, okay, and W is equal to I don't know, U gamma E gamma plus V delta, this may be bad notation, I E delta. Yeah. And now let's look at the extended bilinear form applied to VCW. Okay. I'm following Prabhat's argument here. I'm doing calculation in basis. See what happens here. That means it's the same form. It just is, you know what it is. It's okay. We know that. Well, now let's write it down. This is equal to. Let's see. X alpha E alpha. Get used to it. I E beta. I'm not saying that it's fun to do these calculations, but sometimes you learn something by doing some calculation. And physics friends love to do calculations, so I'm doing some of it. Okay? Now this is the usual extended form, so that means that x alpha E times that is equal to x alpha times U alpha, U gamma, right? X, yeah? Good. And now we extended this thing. These are perpendicular. We extended it that way. So I E beta is perpendicular to E alpha. So these things with I are perpendicular to this. We only get contributions in the I part. And we get I times I is minus 1. But what did I do over here? I put in C. So what I put here is plus because I had, this is a complex bilinear form with plus, I have to put in plus. So if I'm going to do it, this is going to be bar for the complex linear form. So this is going to be C of this vector. And what I get here is bar, is that gives me an I. And so this is y beta v delta. No, y beta v beta. Now I may have butchered that, so I want you to, Nicholas is mannerly and very nice guy. He would not say you were too fast there, but I went pretty fast, right? What I want to do is extend the scalar product to the complexification to be the natural scalar product on the complexification, right? That means I want to have it to be the same thing on VR as I do on IVR, okay? So I want the geometry, the natural geometry is just a real geometry, just extended in a stupid way. Okay? And you see what I ended up doing. You see, I ended up, this thing, if you look at it all, look at all what it is simply the natural extended scalar product on the full real vector space. If you do it this way, yeah, this is Rn, and this is I times Rn, that's the complexification, Cn, and this whole thing is R2n, and I start with the scalar product here as the usual scalar product, then I define a real scalar product here on the full thing, just to be the complex, the real scalar product here, to be the obvious bilinear extension of the real scalar product to this, but with complex conjugation here. Okay? And I did it out for you. That is the extension of the standard scalar product on the real vector space to the complex vector space. I recommend you think about this, because in fact, in your calculations, you've been doing this all your life. You just didn't know what the devil you were doing. Okay? Again, you start with, what is a real vector space? It's the real points of a complex vector space. Good. You start with a scalar product on the real vector space. You start with geometry on the real vector space. It is trivial and formal to extend that to a complex bilinear form on the complex vector space. You just extend it through the scalars. That is some blah blah formal. But what is not formal is to understand that if you put the complex conjugation in the second argument, what you have effectively done is just extended the real structure, a scalar structure, to the complex, to the real complex, scalar structure. So sit down and think about that a little bit. That is the right thing to do. So let's summarize that. Yeah.
Aren't we missing the complex part in that computation there? Maybe when we just write it down, shouldn't we also get
This is exactly the right question. What happened to the eyes? Where did they go? Yeah. Let's do the computation. Look at it again, okay? So the eyes are in here, and I'm taking the scalar product with the eyes in there. That's the first remark. That means I've extended the real scalar product just formally to a complex bilinear here. So this is now complex bilinear. Okay, so I just close my eyes and it's complex bilinear. So it's this times all this stuff here. Okay. this times all this stuff here. So you will see, that's a very good question, Nicholas. It has to be, I mean, what you're asking is why don't I have x alpha times v delta, right? You don't have that because when you look, when you extend it, okay. Okay. When you extend, if you look at what you do, when you extend this bilinear form to the complex space, it ends up that with respect to the complex bilinear form, these two things are perpendicular. Okay? So that says that E alpha, which is in this space, is orthogonal to any IE delta in the other space. So when you have that times that, that vanishes. That's what you were worried about, I think. And when you have that times that, it vanishes. So all you get is that times that, which is that, and then that times that, but there's a bar there, and so it makes it positive.
Oh, so and that only happens in the complex inner product, or in the real inner product.
So what I've done here, this bilinear thing here that I've written down is the complex bilinear thing. And if I put bar in it, it's no longer complex bilinear. I screwed that up, right? But what I've done is to make sure that the inner product I get in the end is my favorite one, by putting the bar in there, the complex conjugation. Okay? A very good question. You always complexify. By the way, quite often you start with a complex vector space and you complexify. Seems crazy, but you must do this quite often. Okay, so this what I'm talking about, this is the Hermitian, this is called now a new word for you. This is called the Hermitian product of V and W. Okay? So the Hermitian product of V and W is you take the extended bilinear form, this is a complex bilinear form, and put in complex conjugation in the second argument. So this form is the C bilinear extension. And you put complex conjugation in the second argument. Okay? And this form is the right form for everything. And now, please read, as I think Deepak did, read Wigner's article. Okay. Wigner, the great physicist Wigner, does not understand how mathematicians came up with Hermitianity as a condition. How Hermite came up with that. You read the article, right? He thinks it's amazing. The article is called, what is it called? The
unreasonable effectiveness of mathematics.
Unreasonable effectiveness of mathematics in the natural sciences, or something like this. Mathematicians, for example, the word Hermitian is named after Hermite, the great French mathematician in the 19th century. By the way, he was really also a very kind man and very supportive of Sonia Kovalevskaya, who was certainly one of the first very outstanding, interesting women mathematicians, who came from Leningrad, and it was called St. Peter's then, and it's called St. Petersburg now. So, but I call it Leningrad because the last time I was there was Leningrad. So she came from St. Petersburg to Germany, tried to study in Germany. It was very difficult, but finally Weierstrass supported her very strongly. She worked with Weierstrass, but had strong connections with the French school in Paris and Hermite, for example. It's called Hermitian, this thing, H is called the natural Hermitian structure on defined by a real vector space, which is a complex vector space equipped with complex conjugation. Okay. And if you do it in coordinates, if E1 through En are let's say good bases, and I'll talk about what good means. I'm good basis. Yeah, it means HEI EJ is delta IJ. Yeah, that's, you can do this. Okay, this basis. And if you write V as equal to Z alpha, E alpha, and W equals Z beta, W beta, E beta, then in that notation, H, you know what I mean, a VW, which is, and you write down what it means, it's the complex bilinear extension of VCW. You see what it is. It is exactly Z transpose W bar. Yeah. Well, everybody knows that, man. Everybody's cool, because if you have complex analysis in one variable, you have Z, and you know the length of Z, squared, equals ZZ bar. It's a miracle. It's ZZ bar. Yes? Is x squared plus y squared in real coordinates, with the real part and the imaginary part being orthogonal and so on. You took, in complex analysis, without even thinking, realize the complex plane as equipped with an involution, complex conjugate, and so it is really the real numbers with an involution. It's a complexification of the real numbers. And you did everything I just told you to do here. You take the standard real structure on the real numbers. Well, you learned that from K-Rod. That's just, length is just absolute value, right? There are no angles, so it's just you have length. You extend that notion in a canonical way to the complex plane, and you get this. I hope I put it through here, you can see it. Okay. All I'm saying is, if you have a complex vector space V, the blackboard's a vector space V, you have the real points in that vector space, you have I times the real points in that vector space. Yes? You have the real structure here. This is the real structure here. You extend it to the complex linear structure here. And then you define the appropriate inner product, which is the Hermitian structure, which is the V of the complex involution of the complex extended bilinear form. There's a Shakespeare play, I think you know it, if you are great intellectuals, which I'm sure you are. I think it is Shakespeare. It's called Much to Do About Nothing. Yes. And you might think this is much to do about absolutely nothing. But I guarantee you, Wigner did not understand it. He didn't understand it because he didn't know where mathematicians got this idea. So the notion of a Hermitian structure comes purely from mathematics, but it is the central structure in at least elementary physics. I think there's no question about it. And this is how it arrives. Okay. So, in the background, physicists have a complex vector space with an involution. Always. Some physicists will say it's time reversal involution. Depends on who the physicist is. They have names for this thing. This is a real structure. And they will go, well, I shouldn't write brackets like this because you think it's a bilinear form. So this is a real structure. And you go to the complex bilinear extension, VW, and this is the complex bilinear extension of the real linear structure here. So this is the real geometry. And this is an extension of the real geometry to the complex space. Yeah, and this is what we call the Hermitian form, the associated Hermitian form. Okay. And now, mathematicians are not in general stupid. Some are stupid, some are not. And so you check what are the properties here of this thing. The property is CV equals CCV W equals WCV. I don't know, you start doing these calculations, WCV, this is equal to HBW. But in fact, you see that CV is equal to CVW bar. And so what would happen here is you got some calculation, and you easily check that HVW is not symmetric. It is using these properties. I'll do very quick here because I find this boring. Is you exchange the variables here, and because of how things are working, you change the variables, and it does that, right? And it's just because of what I wrote here, and it's trivial calculation. Okay, so it's bilinear in the first. I think bilinear in the first variable, of course, because it's linear in the first variable. So it's linear in the first variable, and it's antilinear because you had the complex conjugation in the second variable. Antilinear, the second variable, and it's not symmetric. If you change the order of the variables or the vectors, you pay the price of a complex conjugation. Mathematicians, you will see, name things horrible names. The name you will see associated with this is sesquilinear. Forget it. Forget it. Start with the real vector structure. You understood what it is now. Take a real form on the real thing. Extend it in the only way you can do it. Right? Extend everything in the only way you can do it. You want to recover the real geometry on the complex space. You were forced to be introduced this Hermitian form. So I spent an hour and a half. I wish Prabha were here because he would be convinced that the notion of Hermitianity is natural and doesn't really have to do with coordinates or anything. Okay? This is the notion of Hermitian form. Okay. Anyway, Prabhu's my friend, so I'm happy to have an argument with him. So very soon in the physics ball game and almost immediately in the complex ball game, in the mathematics ball game, when we start with real geometry, we are forced to consider complex geometry because spectrum of operators are complex. Right? Spectrum of operators are complex. Okay, here we go. We start with a real vector space. We start with a real vector space, a real vector space. Equipped with a real scalar product. Scalar product. Positive definite. We get the orthogonal group of this real vector space. If you take a basis, you get the orthogonal group. The orthogonal group. The symmetries of the real positive definite. Oh. T, V, T, W, R equals VW. The involution that is here, that is relevant, is sigma of T equals T minus transpose, T inverse transpose. Fix of sigma in GL V, VR, everything's over the reals here, is the orthogonal group. Standard orthogonal group. Okay? And evolution plays a role. Okay. I told you everybody in his right mind complexifies and goes to a complex vector space. The appropriate complexified structure on the complex vector space is the Hermitian form, which is written. Maybe I'll emphasize CW, and then I'll put C here. This is the complexified extension. This is the extension. This is the C bilinear extension. Of the real structure to the complex vector space. This form is a Hermitian form. Hermitian form, and it is positive definite because the norms that you get are positive. Hermitian has several properties. H is bilinear, is C linear in the first argument, the way I've set this up, and C antilinear in the second coordinate. Yeah. And it is not symmetric anymore, it is anti-symmetric in some sense. Because we put this, well, I didn't write it in, so I'll write it here just, can I write it up above? Oh yeah, it's up above, good. WV bar. The reason that bar occurs is because of the C. Okay. And the norm, of course, is what you think. Okay. What else do you want? And in coordinates, if you like, V equals Z alpha, E alpha, Z complex, W equals W beta, E beta, then H of V alpha, V and W is just Z alpha, W alpha bar. And so norm of VV, that's the norm, is Z alpha Z alpha bar, and that's the same thing as absolute alpha squared. Okay. And now, this is a lecture on symmetry. We look at the symmetry of the Hermitian structure. I've talked about this already, but not today. I'm talking about it more carefully. So symmetry of the vector space, complex vector space with the Hermitian structure. Well, it's really stupid. The group of symmetries is called the unitary group. Of this structure, and it's written, sometimes I write it if I want to write it abstractly. It's the unitary group, it's the group of transformations which preserves this structure. But if the dimension of this vector space is V, is n, and we take, if the dimension of this vector space is n, and you want to not think about this anymore, you have all this stuff implicit in your mind, quite often you will see people write this un. Okay. So, but that, usually that means you're taking a basis, and that's a bunch of matrices. But what we have here is just simply the unitary group of this thing, which is U this. This is the symmetries of this, the set of T in G, L, and C, such that H of TV, TW equals H of V, H of W. All V and W. It preserves the obvious structure. Okay? And we know that in the standard basis, E1 through En orthogonal basis as usual. H, now I'll write everything in a basis, H of ZW, well, H of VW equals V transpose as a vector, W, which now I'll write, W bar, which now I'll write as V alpha W alpha bar. That's that. So as vectors, this means H of VW equals operating on it, it means that V transpose W bar equals V bar T bar transpose, where's bar? No, T bar, T transpose from here, and now T bar from here, W equals, there's a transpose here, equals, it doesn't change, so it has to be V transpose W bar. So that says that T transpose T bar equals the identity. It says, where's a bar? Here's the bar. It says that T equals T inverse transpose bar. Now that's really too fast for you, so I'm going to repeat it. Okay, what did I do there? I'm looking at the symmetries of this form. It means it preserves the geometry. It means it preserves the inner product. All geometry is given by inner product. You write down what it means. It means that. So you write down what it means in terms of operators, matrices, and so on. You write it in terms of these vectors. This inner product here, this Hermitian inner product, is just V transpose W bar. We wrote it here. It's V transpose W bar. So you stick in this thing, and it has to not change it. That means the guy in the middle has to be the identity. Then you write what that really means. You bring the T transpose on the other side, get inverse, and you bring the bar on the other side and get this. Okay? Well, I don't know what I'm gonna call this thing, but I think I'll call it theta of t equals t bar transpose inverse. So the involution theta defines the unitary group, just as the other, remember this defines the unitary group, and what I had before sigma, which was d just equal to t inverse transpose, this defines the orthogonal group. Right? Well, that's interesting. Right? These groups are all defined by involutions, and we have two involutions, and you can check. You should always, you should always check how they are related to each other, these involutions, and you will check and have fun checking. It's very easy. They commute. These involutions. They commute. So that's good, because if you have, it makes sense to restrict the one involution to the fixed point set of the other involution. Because if they commute, then it is clear that the one involution preserves the fixed point set of the other involution, and vice versa. It's incredible. The unitary group is therefore the fixed point set of the restricted involution in the orthogonal group. So that's really what is going on here. These are the two involutions of relevance. And we have now in general ON and UN. And these highly motivated, I hope, groups. Good. So now, again, I'm just repeating almost what I talked about yesterday, but I'm repeating it in a way that you can understand it better, maybe. And the third classical compact group is the symplectic group. But it's the unitary symplectic group. And let me repeat. What the situation is. So everybody in life has a real vector space, so that means a complex vector space with complex conjugation, which my physics collaborator, Martin Simbaugh, from whom I learned a great deal, always calls C. So we start out with this and an induced Hermitian form. So maybe I put it all in one thing. Right? Put it all in one thing. And that's the starting point. And you have two things of interest here. You have an orthogonal group on the real structure, and you have, because the Hermitian restricts to the real structure, gives you orthogonal group, and you have the unitary group, which is really the stabilizer of the Hermitian structure. And in terms of matrices, say this thing is on Rn, this is fixed sigma, and in terms of matrices on the usual basis here, this is fixed theta. Right? And these are contained in real orthogonal groups, so these are compact classical groups. And as n goes to infinity, this is interesting. this is called a series. This is called the infinite series. Two of the infinite, among the infinite series of classical groups. There are some isolated groups which you have seen in movies, maybe. One of the isolated groups is G2. And there are big arguments that G2 is relevant for physics. By the way, we were talking last night of this six-dimensional sphere, this exceptional group. This is exceptional. It has to do with the sphere. There's something called F4, and then there are various groups with E something. These are exceptional groups. They're not in an infinite series, but they do appear in real life. So I participated in a very interesting congress in Banff, Canada, which is a wonderful place to go for both mathematics and physics, and it's in the mountains, which is also wonderful. And the subject of that course was E6. And E6 is it's a very interesting thing to consider, E6. And so, and things around it, not necessarily the compact version, but these groups are important, very important. I don't disregard these groups, but you have these groups are the basic building blocks of compact groups, along with infinite series. Infinite series are orthogonal group and unitary group. Yes?
What are the dimensions of the exceptional ones?
I don't know. I have to sit down and compute the Lie algebra. That's trivial. But by the way, I should just comment. He probably is more closely interested in Lie algebras. I would guess. Well, from the point of view of thesis, I think. I will talk about that. You've heard the word Lie algebra and so on. But that's the way to compute a lot of things about groups. They're defined by involutions. And as soon as you have the involution, you have the induced involution on something called a Lie algebra, and that's just a linear mapping, and you can compute out everything about that. I should comment that these groups here, particularly some of them around this one, was only theoretically discovered by, it had to be, it's one of these things, like it has to be. Let me tell you, there's something called the monster group, which is a finite group. And everybody knew that that monster group had to exist, but nobody had seen it. Yes, everybody knew that the monster group had to exist, but nobody had seen it. And one of the greatest events in group theory was to find the monster group, because it's very, very interesting. It's also related to physical considerations of the so-called Leech lattice and other things. So we had to find it, and great mathematicians found this group. Same thing was true of these exceptional groups. There was a very great mathematician, I think he was the one who found these groups, or was one of these exceptional groups, and was certainly involved with the whole theory at the time. I write his name here. It's very nice because the name, if you look at it, it looks terrible in English. Killing. I'm going to kill you. You know. Right? But Killing is a name from this northern region of Germany, rather near Schleswig-Holstein, and so you see a lot of names like Killing. And he was a great mathematician in Münster. And in Münster, he even became rector of the university and became very, very important. And he was involved with understanding whether these things really exist or not. I can't remember exactly what he proved, but he certainly constructed. It's a question of constructing these exceptional things. Yeah. You know they have to exist somehow, but you want to construct them and prove they exist. Well, that's what we've done. Here we have the two infinite series, and in 8 minutes I'll write the third element of the infinite series again on the blackboard, okay? Well, here we go. So, somebody in Moscow and Japan, Bogolubov in Moscow, who I knew a little bit and I've forgotten the guy's name in Japan, said what you have to do is to go to this vector space. This is the right space for much physical consideration. And one of the reasons it has such great importance is that you have a canonical symmetric form. F-canonical alternating form. I wrote them down yesterday, S and A. You say, oh my God, I start with this thing, I know this is the right space for many physical considerations, so I must understand what this structure here has to do with this space. Okay. So we looked at that stuff yesterday, and we found out that SPW of the alternating form, so I'm emphasizing it's linear transformations on W which preserve the alternating form, and which is called the symplectic group, the complex symplectic group, because I'm talking about complex linear transformation. We write here it's SP2NC in terms of matrices, and I even wrote down what the matrices look like yesterday. Yeah. That's the first thing to consider. And this thing here is not compact. This thing is a beautiful version. Is a complex group. And if you don't believe me, well, it lives inside GL2NC. And yesterday I wrote down the involution. Right? I don't know what to call it now. I've got so many names here. Maybe tau. Tau in my research is a totally different involution, so this is very confusing to me. So, but I'll write the involution on the matrices. Tau of a matrix or a transformation, I hope it is something like this. Huh? I even remembered it, I think, correctly. Yeah. So it's the usual involution here, but conjugated with J. And that's quite often the way you make involutions. You should take some standard involution like T goes to T minus transpose, and you conjugate it. Okay, is that right? Is that what did I get it right from yesterday? Yeah, I think so too. Okay, so that's great. So here we've used the alternating structure. And physicists have told us all along, Hamiltonian mechanics, quantum mechanics, all sorts of reasons to use this alternating structure. So it's very interesting already that we have a complex group here. You see, this is a condition. Tau is a mapping from GLNC to GLNC. It's a beautiful mapping. It's an incredible mapping. I mean, it's highly nonlinear because it's inverse transpose, but nevertheless, fixed tau is a nice submanifold, complex submanifold of GLNC.
I think there is no inverse transpose.
Huh?
I think there is no inverse transpose. It's just
Yeah, I meant to write inverse transpose here. Is that what you mean?
I think there is no inverse.
Oh, there's no inverse.
Yeah, so it's just a conjugation.
There's just transpose.
Oh, there is no transpose either. It's just
No. Do I have to do this again? There has to be a transpose. Yeah. Are you really sure?
it's just PJ equals to JT, right?
Is that what you're saying without any inverse transpose?
Yeah.
Okay, good. This is a wonderful thing, right? Right? It looks very linear even. That's what makes me surprised. Right? So, yeah. So I think that maybe is not quite right, but we'll check it at dinner. Okay. I'd be very surprised if it's linear. Anyway, it's a very nice submanifold of GLNC. And then you want to go to the induced unitary structure. Now this is an alternating structure, and a unitary structure is really very close to a real bilinear structure and not a symmetric structure. And so we need to go to an interesting Hermitian form, and I'm going to define it for you. The interesting Hermitian form is, well, defined by C. Now, finally, I say, what is a complex structure? Conjugation. It is an isomorphism of V to its dual. Why is that? Well, I take a vector V and I map it, well, a vector V, and I put in here, put in here H of V, where is the linear? The first argument, okay, W. I put a vector W in the second part of this Hermitian thing. W goes to H of W. Right?
I'm sorry, what you wrote was correct.
Huh?
What you wrote before was correct.
Really?
Yeah, the inverse transpose.
Yeah, I hope so. There's no way in the world that that can be linear. Okay. Yeah. It has to be something highly non-trivial like that, right? So, okay. So look at what C is. C defined H. Remember, you start with C, you get H, and all that stuff. And so always we have this triple in physics or mathematics. We always have this triple. So C is really effectively, I'm calling it I'm changing notation. It's a mapping from the complex vector space to its dual. Do you understand what I mean? I put W in the second spot and fix it, and this is a linear in the first argument. So this maps a vector here to a linear function. And in fact, it's an isomorphism. Okay? So that's C. Right? That's C. That's great. Or H, it's the same thing. And now, I'll leave you, let you have some fun at lunch or tonight after you're smoking a cigar and drinking cognac. So I'm going to look at the symmetric form V, C, W. Yeah. I did two things. I looked at the alternating form, and I'm going to look at something that should be background unitary structure on this vector space, new space, which is W. I start with a unitary structure on V, or a real structure, and a Hermitian structure on this thing, and then I get this W, and then I get H, and then I get an isomorphism to the dual space. That's the same thing as above. And this is linear in the first argument, antilinear in the second argument. So this is an antilinear mapping from V to V star. And the way you should think about it, this is a mapping from V star to itself, from W to itself. It's a real structure on W. Namely, you map V to V star and V star to V. Just reverse it. It's completely symmetric. So this thing is really, I'm now calling C. And I put C in the bilinear thing, just as I did before. Right? I put it in here. And what do you know? This is a positive definite Hermitian form. This is a positive definite Hermitian form. Hermitian form on W, twice as big. And it defines the unitary group on W. So I don't know what we want to call this. We have the unitary group, I'll write it here, just the unitary group of W. You know what I mean with all of this stuff. Well, I'll just write W, C, and so on. Okay? That's very interesting because this involution you can write down. okay? And this involution is, if you write it down, oh my God, I have so many involutions here, it's not even funny. This is tau is this one. So the U is defined by, I'm going to try to make a guess here. By probably, maybe it's simple-minded. T, I don't know, that is something like T goes to T bar transpose. There's probably a J involved, you have to look. Okay? Look, take the basis and look and do it. And this involution, which maybe you want to call tau alpha, and tau commute. That means the fixed point of alpha, which is the unitary group, yeah, makes sense to talk about restricting alpha to the fixed points of tau and looking at the fixed points of the related thing. And the fixed points of the related thing are the intersection of the two groups. And so, let us say, fix alpha on fixed tau. This is equal to the intersection of this unitary group, W, etc., 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 to the intersection to the symplectic group of this thing. And this unitary group is a compact group. This is a complex, wonderful affine manifold and so on. It's not a compact group, but this is compact, so the resulting is a compact group, and this is called USP2N. Okay? So in almost exactly 2 hours, I've written down any number of involutions that commute, and they define all the classical groups. And you can write that down. You can write down what the operators are, and you can write down therefore the equations of the manifolds of these groups, and you see that of course they're compact. And the differentiable manifolds, they're smooth. Yes, so they have smooth structure, and therefore they are called compact Lie groups. Okay, so I'll start talking a little bit this afternoon about how you deal with these groups. Okay, so you've seen, if you believe you've seen a little bit about the exceptional groups, you've seen all compact groups. Finite groups, products of tori, these groups here. Okay. Of course, you should take the S part, so the determinant equals the 1 part. That's no. So this is very much for somebody in beginning mathematics, but it gives you a look at what you ought to look at. Okay. See you this afternoon. Thanks for your patience this morning.